Introduce the next speaker. He is Professor Subhashish Ghosh. He is a physicist. He is a senior faculty at IMSc in physics, theoretical physics, and he is going to, so his PhD is from ISI Kolkata, and he works in quantum information theory, quantum optics, and quantum communications, and various other things, including foundations of quantum mechanics. He's recognized for his work in local distinguishability of quantum states. I will not take more time in introducing him, because we are all waiting to hear him. So he is going to talk about can a tennis ball penetrate through a brick wall? The story of macroscopic quantum tunneling. So we have all heard about microscopic quantum tunneling, and he's going to talk about macroscopic.
Okay, so let me thank this Tamil Nadu Science Forum, TRG, and then Dr. Vijayan, and also the chairman of this session. So what I am going to talk about is something called macroscopic quantum tunneling, although I will not go into much details because I will have to introduce a lot of things. I presume that the audience is a kind of mixed audience, so I will have to talk a little bit about quantum theory, then what is the idea of tunneling in quantum theory for microscopic system like electrons, photons, etc., and then how to go about macroscopic quantum tunneling. Okay. And if time permits, I will talk little bit about applications of that. Okay. Right. Okay. So I said, can a tennis ball penetrate through a brick wall? Of course, all of you say that no, it cannot. Okay. Because the energy of this tennis ball is much less than the required energy to penetrate through the wall, brick wall. Okay, so it cannot. So I guess all of you are aware of this long jump phenomena, right? There's jumper who runs and gains momentum, and then eventually jumps on the top of this rod. Okay. But there are times, in fact most of the times, the jumpers get stuck here. Okay. And what is the reason behind this? Because the energy that this this player has gained just before arriving this rod is not enough to cross that height. Okay. And this height corresponds to height from the ground. It corresponds to some kind of potential energy due to gravity. Okay. So this person, generally if he or she doesn't cross this, which means, generally maybe that he or she has some some psychological issues. I am not talking about that, but mechanically this player should have the enough energy to cross that height, which corresponds to some potential energy. Okay, right. So the point is that this is not, of course, the idea of tunneling, but just to mention that if you want to cross this height, which is called a potential barrier, you need enough energy to cross that, otherwise you cannot do. Okay. So this is what we agree, all of us agree, when we talk about classical world. Classical world means the world where we live in, where the laws of classical physics like Newtonian mechanics, thermodynamics, optics, sound, this, that, etc., all are valid. So laws of classical physics does not allow this jumper to cross a height which corresponds to a potential energy higher than the mechanical energy of that jumper. Okay. Quantum mechanics defies that. So quantum mechanics tells you that yes, it is possible for a quantum particle to cross a potential barrier where the potential barrier corresponds to the potential energy which is less than the total energy of this quantum particle. So, this is why we call these as tunneling. So, there is some region on the right side of your barrier which is inaccessible by classical system, classical particle, but if it is a quantum mechanical particle, it is in principle possible to cross that barrier, and that is why we call it as tunneling. So, tunneling per se is a quantum mechanical phenomena in nature. Okay. Right. Now, people have seen right from the beginning of advent of quantum theory, in fact, after some time after they started experimenting, that yes, tunneling happens for for microscopic system like electron, proton, etc. So, the first example was alpha decay, where alpha particle from nucleus it can come outside of the nucleus, there is a potential barrier, it can come outside of that, okay, and you can detect it, and this is due to this tunneling. Okay, so there are other examples also. The question is that can such a tunneling phenomena occur if I take a macroscopic object which behaves quantum mechanically. Okay. So, the first question is, why do you look for that? I mean, what is the need for going to macroscopic quantum tunneling? Okay. So, the first thing is that we the physicists believe that our whole universe is governed by quantum theory. Okay. Even if at this point of time we cannot prove it experimentally, still we believe that world behaves quantum mechanically. Classical laws of physics are subsets of quantum theory. Okay. They are included inside quantum theory. So, that is a belief, and so that is the primary thing. So, based on that belief, we want to explore more and more macroscopic objects, the quantum features of macroscopic objects. So, that is the first thing, and of course, there are technical reasons for that. So, these days people talk about these quantum technologies and all that. So, there because it is application side, you need macroscopic quantum mechanical effect. Okay. So, not just confined to microscopic system like single electron, single photon, or a bunch of electrons, something like that. Okay. So, so this is the motivation. Okay, good. So, let me now just try to briefly outline what is it that I am going to talk about. As I said, because of the mixed audience, I will talk briefly about quantum mechanics, and then this notion of macroscopicity in quantum theory, because there is not much unanimity about the idea of macroscopicity when you talk about quantum mechanics. But I will talk about specific kind of macroscopicity here. And then Anthony Leggett, back in 1980s, Anthony Leggett got Nobel Prize, I think in 2002 or 2003 in physics. He is a theoretical condensed matter physicist. So, he came up with this idea of Leggett program. I mean, he called it some program, later people called it as Leggett program. So, this is something like Langland's program in mathematics. Okay. So, it is a long term program to figure out whether macroscopic properties are valid in quantum theory. Okay. So, that is what he has given. So, I will talk about that briefly, and then I will briefly also talk about potential candidates where one can get to see experimentally macroscopic quantum tunneling. Okay. What are those candidates? And then I will go to to the discussion about this last year's 2025 Nobel Prize in Physics, which was given for observing macroscopic quantum tunneling in superconducting circuits. Okay, and then as I said, briefly talk about the applications, and I have one or two references. If you want, you can take a look at it. Okay, so let's start with quantum mechanics. Okay, good. So quantum mechanics, I could have given the history of quantum theory, etc., but I guess let us not look into that. So let's be operational. What is it that we need to understand this discussion today? Okay. So like in the classical world, when we talk about a moving car, what is it that I need to know to describe that car? We need to know, for example, is mechanical parts and all those things, how the car has been built. Then if I want to know the dynamics, I need to know what is the speed of the car, if it is moving on constant velocity. If it is not, I need to know the acceleration. So therefore, I need to know how much distance it has covered given a time. Okay. So all these things I can figure out. So when we talk about state of that car, it means conglomeration or accumulation of all this data. That can be static, that can also be dynamic. Okay. So quantum mechanics is also about states. So if you want to describe an electron of an atom, or say a photon which is passing through fiber optical cable, or let us say a DNA molecule, what you need to know is how to come up with a list of observable quantities, values of observable quantities, which will be enough to describe completely the property of that quantum mechanical system. Okay. So that is what is known as state, right? And we generally in classical system we don't talk about state, but it is implicit there. Okay. Now in the classical world, two objects are always distinguishable, like this box and this sound box. They are always distinguishable. Okay. Whatever be your method for distinguishing them, whether to look at their colors, look at their size, or whatever, they are distinguishable, right? Okay. Now the point is that to distinguish these two objects, you don't need any atomistic measurement. You can, like you want to figure out how many atoms are there, and then you distinguish. Or you can try to figure out what are the interactions among the atoms there, what are the interactions among the atoms there, you can distinguish. Or, so this is what is known as fine grained measurement, okay, atomistic measurement. Or what you can do, you can look at their just size, and that's enough to distinguish them. Okay. So when we talk about this transition from quantum mechanical world to the classical world, quantum mechanical world means the world where laws of quantum mechanics are are satisfied, they are used, and classical world means where laws of classical physics are used. So when you go from the quantum world to the classical world by studying properties of some physical system, so one particular aspect one should look into is that this notion of distinguishability. So whether two states are distinguishable by coarse grain measurement. Coarse grain measurement means where you don't look into the atomistic results. Okay. So whether like this height or color, those are coarse grain measurement, not atomistic measurement. So if two states are distinguishable via any coarse grain measurement, okay, in the process of from classical to quantum, from quantum to classical transition, then we say that this is actually it has achieved a classical system or macroscopic system. Okay. In quantum world, when we talk about states of, let's say, single electron, spin of electron or polarization of photon, then this idea of coarse grain measurement does not hold good, because if you use that, you cannot distinguish most of the times the states. Okay. So, in order to distinguish states of microscopic systems, that means states of quantum mechanical system, for example, you need fine grain measurement. Okay. Right. So, therefore, so that is fine. So, because states are distinguishable like this box and this box, we cannot talk about like superposition of these two. What does it mean? Nothing. Okay. You cannot have superposition of, let us say, an apple and a potato. What does it mean? Nothing. Okay. But if we go to the quantum world, microscopic world, it does make sense to talk about superposition of different states. When they are distinguishable, that makes sense. Even if they are not perfectly distinguishable, still that makes sense. Okay? Right. Now, this superposition of states in the microscopic world, in quantum theory, is part and parcel of it. Okay? So, you cannot talk about quantum mechanics without assuming this superposition of states. Okay? So, if you are mathematically minded, you can say that state space of your quantum system is a Hilbert space, and because it has vector space structure, any two superposition of any two states will be again a state. I mean, up to normalization that you can do. Okay, right. So, for example, you can take spin of an electron. So, it is a spin half particle. So, it can have plus half or minus half. So, if you take spin of an electron, which can be prepared. So, somebody can prepare it in a state which is a linear superposition of up and down spin states, like this up spin and down spin. So, these are the coefficients which are complex number, add up to 1 for normalization. So, this is a generic state of spin of an electron. Okay. So, up state is also a valid state, down state is a valid state, the superposition is also valid state, which is not the case in the classical world. Okay. Right. So, states means in quantum theory is all possible superposition of distinguishable states. Up and down are distinguishable states. All possible superposition of distinguishable states they form the state space. Those are the states. Now, state is the primary thing. Then you have to observe, like if you look for a moving car, you have to figure out what is the speed of that car, how much distance it has covered, so on and so forth. Okay. So, if you want to figure out that, then you have to measure some quantity like the velocity or the distance, so on and so forth. Okay. And these are called observable quantities, both in classical world as well as quantum world. Okay. Right. These are called observable quantities. So, for example, you can have energy, linear momentum, angular momentum, spin, spin polarization, photon polarization, everything. These are all observable quantities, these are measurable quantities. Okay. Now, the point is that these observable quantities, when you measure on your system, they will come up with some real values like energy, momentum, linear momentum, angular momentum, whatever. You will by measurement, you can only get real values of that observable, and those are real values. Okay. Right. Good. Now, the point is that you are not sure beforehand that what particular real value you are going to get. For example, if I perform spin of an electron along, let us say, z direction, it can have the spin value, one can come up with this spin value, this is h cut is this Planck constant, or minus of half h cut. Okay. One of these two, which one will come up with, we do not know. Okay. So, here I must say that if you toss a coin, right, let us say a fair coin, unbiased coin, so you can get head or tail, right. you can say that there also this uncertainty is there. Before the measurement, you cannot say that whether it will come out as head or tail. So what is big deal with these values, of the spin values, measurement of spins, okay, of an electron. So there is a basic difference. What is that difference? If you think about tossing of a coin, if I know beforehand how much force I have applied on this coin to toss it, what is the air resistance that this coin will face after tossing, what is the reaction of the ground when it will fall on it, and what sort of dynamics it will follow. So if I know everything, then before it falls on the ground or even before tossing, I can tell you what will be the outcome, whether it is head or tail. Okay. So in this sense, any such experiment, any such quote unquote non-deterministic result in classical world is inherently deterministic. So it is our ignorance that we cannot tell beforehand that whether it will be head or tail. If I know everything about the dynamics of this tossing of a coin, I can tell you, beforehand. This is what is not there in the quantum world. So in quantum world, generically, you cannot come up with an underlying theory like this knowledge of force, etc., which you call as hidden variable. There cannot be an underlying theory which will tell you beforehand that what will be the outcome of the measurement. Okay. So this is the basic difference, one of the basic difference between quantum world and classical world so far as measurement is concerned. Okay. Right. And because we need this kind of different values, these are basically eigenvalues, right. So you cannot say that the energy is just a number. So you will have to come up with mathematically some operator which we call as Hermitian operator, and this is nothing but a square matrix. We have some size n, n is the dimension of the system, so that this is sorry for this little bit of mathematics, this is basically these are the complex conjugate of the jkth entry of this matrix is equal to kj, okay, a kj. Okay, so this is the hermiticity property of the matrix. So, and it is matrix, that is why it has different eigenvalues, and this corresponds to the eigenvalues of this matrix. When you measure, you will get this one of these eigenvalues. Okay, good. So that was about observable. Now dynamics, like classical system, like moving car, we should provide dynamics of a quantum mechanical system. Okay. So the dynamics of a quantum mechanical system, if it is a closed, that means it does not interact with its surroundings, then this dynamics is reversible dynamics, in the sense that if I give you the initial state of the system and the dynamics, then it will produce the final state. If I give you the final state of the system, you will get to know the initial state uniquely. So this is a reversible dynamics. Okay. And also it is a kind of, so the it has this symmetry. So we call it unitary, Wigner's unitary anti-unitary theorem. So where the symmetry of any transformation that you give, it should be a kind of symmetry preserving transformation if it obeys certain rules. So in simple terms, the angle between two states like psi 0 and phi 0, which is the initial state, it should remain invariant under the dynamics. So psi, this is the angle, this is called inner product. So this angle must be same as the angle at later time. Okay. And these two things are basically governed by the Schrodinger dynamics, which is a unitary process. Okay. So the evolution is given by a unitary process. So psi of t is obtained from psi of 0 by the action of this unitary operator. So this is the definition of unitary operator. In fact, Schrodinger equation, which is the dynamics of quantum mechanical states, which is this equation. So H is your Hamiltonian, which is again a Hermitian operator acting on the time evolved state, and this is the time derivative with IH cut, okay, and this is the unitary which is generated by this Hamiltonian, okay, right. So this is my dynamics, okay, good. Now quantum systems like classical systems they can be also correlated, okay, right. So for example, you can have like this a spin half particle A, which is found in this up state, for example, can be correlated with another spin half particle B, which is found in the down state, and vice versa. Okay, so then joint state of this, so psi AB, it will be basically of this form. I have chosen a specific coefficient for normalization. You can choose alpha beta here also. Okay, so this is the up spin state of A spin half particle and down spin state of B spin half particle, plus this is the superposition, down spin state of A spin half particle and then up spin state of B spin half particle. This is called tensor product. You do not have to bother much about that. This is something like product, okay, not exactly product, something like product. For composite system, composite quantum system, we need this tensor product structure. Okay. Now, so this is the so basically all these macroscopic quantum features, they originally came from this notion of Schrodinger's cat. Okay. So the Schrodinger's cat is a funny thing. So you take, for example, a cat in some box, and it is confined in that box, and then there is some radioactive element, and if so it's a poisonous element. So if it if radioactivity happens, so if the element decays, then there will be poison, some poison bottle will be there, and that will be broken and the cat will die immediately. And if it does not, if the radioactive decay does not happen, then the cat will remain alive. Okay. So this is basically, we say that the superposition of dead and alive cat. Why cat? Because cat is a macroscopic object. So when you talk about macroscopic superposition in quantum mechanics, generally this is what we talk about. Okay, although it is impossible still now to realize superposition of dead and alive cat, but this is the so here you see that this is the, so I said the cat which is alive, the corresponding I mean the radioactive element, it does not decay, and therefore its state is 1. This is what I call alive cat, and radioactive element is in undecayed state, and dead cat and the radioactive element in decayed state 0. So this is the superposition of, and again tensor product is there. So this is the composite system state. So this is again superposition, but here you see that this is kind of macroscopic superposition, because cat, alive cat and dead cat are macroscopic states. Okay. So in general you can talk about n spin half particles which is prepared in these superposed states. So all these spins A1, A2, An, these are either in the up states or all of them are in the down state, and n can be arbitrary. Okay. So this is the macroscopic superposition. This is one example. You can have plenty of other examples. Okay. So what is the problem here? Problem is that creating such a macroscopic superposed state is indeed a very, very challenging thing. Why it is a challenging thing? Because quantum systems, whether it's single electron, single photon, 2 electrons, 3 electrons, whatever be the case, they start interacting with this environment. So let's say I have a metal has these surface electrons. So when we talk about individual electron in the surface of the metal, it interacts with the surroundings, which are basically the other parts of the metal, right. So quantum systems are very much prone to interactions with the environment, right. So as a result, keeping such superposition is very difficult, because it requires keeping their coherence. I will come to that. So the question is that, So, therefore, this is what is known as environmental decoherence. So, environmental decoherence is a big hindrance for existence of such macroscopic superposition. Okay? And this is also one of the reasons why it was very challenging to experimentally verify macroscopic quantum tunneling, not just because of superposition, but because of environmental decoherence. Okay, good. So now we talk about the measurement. So, quantum theory is an abstract mathematical theory about physical world. What do you connect with the real world? Through measurement. So, I perform measurement on my quantum mechanical system. So, as I said, measurement of some observable A. Okay. Let us say I talk about d-dimensional system, D can be 2, 3, etc., infinity also, fine. Okay. 2 in the case of Sminha particle, infinity in the case of, let us say, quantized radiation field, for example, or quantum harmonic oscillator if you want. So, this measurement of this observable, when the system has been prepared in some state psi, right. So, this gives rise to, measurement outcome will be one of the eigenvalues of this observable. So, this is the postulate of quantum mechanics, what quantum mechanics tells us. So, measurement of this will give rise to one of the eigenvalues of this observable, okay, and with the probability. So, this is my state, initial state, and this is the corresponding eigenstate, jth eigenstate of this observable. So, this is the eigenvalue equation which is being satisfied by this observable, which is a Hermitian operator. Okay. So, this is what is known as Born rule. So, Max Born came up with this rule, for probability rule. So, therefore, measurement in quantum theory is not deterministic and it is inherently probabilistic in nature. So, these probabilities you cannot avoid these probabilities, okay, right. So, now the point, so and after this measurement the state of this system will collapse into the corresponding eigenstate. Okay. So, this is, and this collapse happens immediately after this measurement, and this is where we break all our heads to come up with a dynamical description of this collapse model of measurement. So far, no success. Okay. So, we take it that collapse happens. How collapse happens, we do not know. Okay. There are some models, but experimental verification is still far away. Okay. Some people use gravity induced collapse and all that. Okay, good. So, now the question is that when you consider macroscopically superposed states, what happens is that we generally consider that environment is there which is interacting with my quantum system, and due to this interaction environment selects a particular basis. So, this is what Zurek called this as aim selection. So, environment selects a particular basis, and in that basis the system has been measured, and as it is measured, so let us say this basis is this up and down spin, then once it is measured you will basically boil, and if the outcome is this up, for example, then the state will become this product state, no superposition is there, okay, or it can be also this down state, no superposition is there. So, that is the problem of environmental effect on macroscopic system. It can have also effect in microscopic system, but macroscopically it is more because the environment most of the times it will act jointly on all these systems together. Okay. So, the question is then you need to do measurement to know about the system. So, if you do measurement it will disturb your system state, but through measurement only you can get information about it. Okay. So, there is a dichotomy. In order to get information about quantum system you will have to perform measurement, and if you perform measurement it will definitely disturb the state of your system. Okay. In classical world nothing like that happens. In principle I can come up with a measurement process which will not disturb my classical system. Okay. So, this disturbance, measurement disturbance is inevitable in the quantum world, you cannot avoid that. Okay. right. So, this is sometimes useful, sometimes it is bad, right. Okay. So, now, so we discussed about the basic ideas about quantum theory, states, observables, dynamics, measurements, composite system. So, these are the building blocks of quantum mechanics. Okay. From here, you can learn quantum theory in principle. Okay. Right. Now, let us talk about quantum tunneling. What is it about? Okay. So, let us say I take a one dimensional quantum system, you can take 3 dimensional. So, to make our life easier, let us say I have a quantum harmonic oscillator which is moving along one direction, x axis for example, right. Let us say its mass is m, okay. It has mass m, and let us say it is under the influence of some barrier potential. So, you can think of this barrier potential like the height of this rod, okay. Is under the influence of some barrier potential which is function, which is basically potential energy, function of x position, right. And let us say that the state of the system, this is called wave function, state vectors are vectors, and then you take representation of those state vectors in certain form. So, like here it is the position representation of the time evolved state vector, so which is I call as psi x t, and this gives you basically what is it. So, if you take mod square of psi x t, okay, it gives you the, and then multiply of course by dx, because this is continuous variable, x is continuous variable, t also. So, mod square of psi x t times dx gives you the probability of finding the particle near x at time t. Okay. So, that is the probabilistic interpretation, Born's rule, right. So, let us take first the infinite barrier. I should have drawn some figure, but let us say. So, this potential is such that it is very large, infinity plus infinity, okay, for x less than 0 and also for x greater than L, and within this region 0 to L it is 0, potential is 0 there. So, it behaves like a free particle within this box. Okay. So, here you can show quantum mechanically, if you solve Schrodinger equation, that and this is also evident from this potential, that the probability of finding the particle outside of this box 0 L is 0. So, if you put a detector outside of this barrier, you will never find the particle there. Okay. So, this is the infinite barrier potential. So, the question of tunneling does not come. Once you confine your particle within this infinite barrier, it cannot come out of that. But if you have finite barrier potential, like V of x is some finite quantity, some positive quantity V naught for x less than 0, also x greater than L, okay, and 0 inside this box 0 to L, right. Then even if your initial wave function is 0, let us say for x greater than L. So, on the right side of the box, the probability of finding the particle initially was 0. Nevertheless, via the Schrodinger evolution, via the dynamics of this process, you will find the particle on the right side of the box with some probabilities, because this will become non-zero. And this is what is meant by tunneling, okay, in the sense that your total energy, if this V naught is, if it is greater than the total energy of this quantum mechanical system, if you start with, still it can cross the barrier. So, this is what is known as tunneling. Classical world, it never happened, as I said, okay. And for example, as I said, quantum tunneling is responsible for alpha decay and probabilistic nature of radioactive decay. So, radioactivity happens with probabilities. You can figure out what probability it will happen, fusion process in sun, etc., etc. So, there are plenty of phenomena which can be explained through quantum tunneling. Okay, good. But interesting thing is, and this is where this Nobel Prize is important, that quantum tunneling has also been observed in superconductors and semiconductors. Now, if you are not aware of superconductors and semiconductors, so these are basically physical systems, like some typical like niobium oxide or something. So where basically if you pass current, we know that because of resistivity, current can pass, but it will produce heat. Okay, so because of the resistivity. So if you keep the temperature of that system lower and lower and lower, what happens is that the resistivity, current can pass through without any resistivity. After, below certain temperature, which we call critical temperature, current can pass through. Okay, and these kind of systems are called superconductors. Okay, semiconductors are in between superconductors and insulators. Insulator are those objects through which current does not pass, and semiconductors are in between. Okay. So, quantum tunneling has been observed in semiconductors and superconductors, but not at a macroscopic level. Okay. Right. So, in fact, in 1973, this Physics Nobel Prize was awarded half to these two experimentalists, Leo Esaki and Ivar Gever. So, they have done these experiments on quantum tunneling separately. Esaki has done quantum tunneling with semiconductors, and this Gever has done on superconductors. Okay, right. And in fact, this experiment on quantum tunneling on superconductors, which was done in 1960s, they actually basically confirm that there is an energy gap in superconductors. Earlier people used to think that this is a continuum of energy, there is no energy gap between the ground state and the first excited state kind of thing. And this was actually predicted earlier by these BCS, John Barden, Leon Cooper and Robert Schrieffer. So, back in 57, for which they were also given Nobel Prize in 72. Okay, this is what is known as BCS theory of superconductivity, low temperature superconductivity. The other half of this 1973 Nobel Prize was given to a theoretician, Brian Josephson. Okay, and this was given for this theoretical prediction regarding Josephson junction, regarding quantum tunneling via Josephson junction, what we call today. And these are basically this Josephson junction, the quantum tunneling through Josephson junction is very much important to the award of Nobel Prize of last year, okay, for macroscopic quantum tunneling. Okay, so that was about basics of quantum mechanics. Let me go to this macroscopicity. So now from now onwards I will not go into details. So this notion of macroscopicity in quantum mechanics is there is no unanimity about it. There are different ways of understanding notions of macroscopicity. So this is this famous experiment of Young, which is called Young's double slit experiment. So here is a source of light or source of electrons, whatever you can think of, and then it is so through this single slit it is coming, and then you have a plate with these two slits, S1 and S2, and then you can think of like wave is coming, and then there is detector on this screen, and you detect these particles, and then you will look at this intensity pattern. So it will look like this if it is light. So on these detectors you will see this bright area and the dark area. So these are called bright fringes for constructive interference of this wave, and dark fringes for destructive interference. Okay, right. So so one can say that, and this is the this is one of the very basic idea about understanding superposition in quantum mechanics, superposition of states in quantum mechanics. So this interference happens because of superposition of states corresponding passing through the up slit and down slit, otherwise interference you do not get to see. Okay, good. So now as I said, there are different types of macroscopicity. So if we look at here, it can be single electron or single photon passing through either this slit or this slit or this slit. But still their states can be macroscopic in nature, in the sense that the distance between these two slits, I take it very large, and this is something like distinguishing these states through the distance, and which is a macroscopic distance, and therefore in principle you can use coarse grain measurement. Okay. So therefore these states corresponding to these slit 1 and slit 2, they can be macroscopic states, macroscopically distinguishable states, you can say that. So even though there is only one particle. But here I will not talk about that kind of macroscopicity, I will talk about real, in an actual sense macroscopicity, in the sense that these are just bunch of lots of particles are involved in the system. Okay, right. So, so this interference pattern, as I said, this is due to this superposition. In fact, this Young's double slit experiment, when it was initially thought of, I think it is 1801, something like that, when it was given. It was not experiment, it was a theoretical thing, and then it took ages to actually verify it experimentally. Okay. So people have seen this Young's double slit experiment with electrons, neutrons, like helium atom, neon atom, sodium atom, etc. And not even that, they have seen it for this carbon 60, C60 molecule, which consists of the 60 carbon atoms. So as big as C60, you can look at that. Okay. So the interference happens there, right? Okay, good. So now, as I said, that the main hindrance about observing macroscopic superposition in the quantum world is due to the environmental decoherence. Okay. So let's say I have these these things. So that I have these macroscopic like experiment. So let's say I have two states which are macroscopically distinct states. Okay. So macroscopically distinct means that by using coarse grain measurement you can distinguish them perfectly. Yes. Sure. Okay. So you have these two distinct macroscopically distinct states, something like this. Psi is this one and psi prop is this one. These are orthogonal states. Okay. Right. So what happens is that due to interaction of this macroscopic system with this environment, so even if you start with this superposed state, like linear superposed state, ultimately what happens is that, so this is the coherence I was talking about. So these cross terms with so this is a real part of the inner product of psi and psi perpendicular. Oh sorry, this is will be 0. So anyway, so you can take some non-orthogonal states also. So because this will be 0, but you can take some non-orthogonal state, macroscopically distinguishable states. So not necessarily orthogonal states. So anyway, so what happens is, because of this environmental action, this linear superposition will boil down to mixture of such projectors. Okay. So this is a classical state, no coherence is there. Now there are different models how this decoherence happens. In fact, Anthony Leggett with his PhD student Amir Caldeira back in 1978, they came up with a model of decoherence, environmental decoherence, which is nowadays we call as Caldeira-Leggett model, where your system interacts with environment, where the environment consists of bunch of non-interacting quantum harmonic oscillators, okay, at some temperature, right. So what the challenge is to overcome this decoherence effect, maybe by cooling your system so that there is not much effect of the environment, or maybe by some other controlling method. Okay. So I will not go into much details, but this is a kind of logical steps, as I said, is like something like you can think of like this Lagrange program in mathematics. So this is what we known as the Leggett program. Okay. So which is about testing quantum mechanics from the context of macro realism. So, basically what it says is that there is no clear cut boundary, that as I keep increasing my system size, at what level the system will start behaving classically, okay, starting from quantum theory, quantum mechanically. So, the question is that because there is no clear boundary between the classical and quantum world, what can happen is that you can still get to see experimentally these quantum interference of macroscopically distinguishable states, okay. That may be possible. So, keeping this in mind, what Leggett has done around 1980s, he has given this program, okay, and he has actually himself pursued it to a great extent. So, what is this program? So, basically you look both via experimentally as well as theoretically for macroscopic quantum systems to show evidence of this QIMDS. So, QI means quantum interference of macroscopically distinguishable states under some appropriately controlled environment. Okay. So, this is the first question. If experimental result, results can be interpreted via quantum mechanics to show this evidence of QIMDS, proceed to step 3. I will tell you what is that step, and if it is denies the existence of this QIMDS against quantum mechanical properties, maybe you have to quantum mechanics is perhaps not applicable for macroscopic system, perhaps, okay. But so then what you can do is verify without invoking quantum mechanics whether your results, experimental results, are compatible with the macro realism. So, what is the macro realism? Macro realism tells you, just like macroscopic system, that a macroscopic system can have specific values corresponding to its observables, specific set of values. If I measure, I will only get those values, and even if I do not measure, the system will have one of those values only. So, this is what is known as one part of macro realism. The other part of macro realism is non-invasiveness of measurement. So, I can in principle measure some observable corresponding to macroscopic system without affecting the post measurement state of the system. So, that is what is known as non-invasivity. So, these two consist of this macro realism, and you can imagine that any macroscopic system will have these properties, okay, right. So then if yes, if this if it is compatible with macro realism, so basically you cannot the experiment cannot decide between quantum mechanics and macro realism. So, go back to step 1, whatever. So, the question is, Leggett has come up with this set of rules which tells you how to judge whether quantum theory has evidence for macroscopic systems or not, okay, and how to do that step by step, okay. And based on this macro realism, Leggett and his another student Anupam Garg, they came up with some statistical inequality which involves time correlated measurement. You measure on your system, evolve it, again measure some observable. So, this time correlated measurement statistics has been used to generate some inequality like Bell inequality, whose violation will tell you that macro realism is not valid even in nature, and there are several such violations that has been observed. Okay. So, I will not go through these details. So, this is one particular example, this is called superconducting circuit. So, you have this niobium material in this tube, and this is superconducting, but here you have some aluminum oxide, so small one, which behaves like some kind of insulated. So, current here it is superconducting, no resistance, but when it passes through here, there is some resistivity, and this has been used in this 2025 Nobel Prize experiment was done back in 80s. So, this is called superconducting circuit. So, this has been used to show tunneling, and what is the tunneling? Basically, you put basically a voltmeter here, so that you can see the current passing through this. So, this current they can manage to detect, and that tells you that you have basically tunneling here, and because it is superconducting system. So, this is a quantum mechanical system, this is also macroscopic, because you have some finite size here, and so you have a tunneling here through this barrier. This can be thought of as a potential barrier of macroscopic system. How large it is, it depends, it's not that big, but still it is macroscopic in nature. So, this is what is known as QUID, so the superconducting quantum interference device, and this has been used in this 1980s experiment by these three people, John Clark, Michel Debré, and John Martinez, who got the Nobel Prize last year, to show this. And here what are the challenges? So, I will not go into all the details. So, basically the challenge is, let me talk about this. So, the challenge is that this is a quantum system, it has environments like particles of this thing or outside. So, due to which the superposition will get lost to some extent, but superconductors has this property that their resistivity is almost 0. So, therefore, you can get rid of that environmental effect, but the problem is that there is some ambient temperature here. So, whatever current you can get to see, it may be due to that temperature effect. So, you will have to get rid of that temperature effect, that they have done by reducing the temperature, but on the top of this thermal fluctuation due to temperature, there can be some other background fluctuation, maybe due to microwave radiation or whatever. So, that background fluctuation again they have reduced by some technological development, and therefore, they established through experiment, they have series of experiment, I think 3 at least, they established this macroscopic tunneling quantum mechanically. So, so maybe I will stop here, I will not go into. So, this is the you can look at the Nobel Prize official document, and this is a very pedagogical book on this macroscopic quantum tunneling. Of course, it does not talk about this Nobel Prize winning experiment, but it gives you some idea about that. Thank you.
Okay, so we'll take a few questions. Thanks a lot for such a interesting talk. I don't know much about it, but I'll still have some questions. But first, other people.
It is way beyond my perception, sir. Obviously, I come from a very different field, but I was wondering if there is, a real world application where this would, it seems like I was just watching Avengers and we had just gone time traveling. I don't know. I mean, it sounds very, very, sophisticated. So, what would be in your imagination, or if there is something that is real world as an application for this?
Yeah, so I didn't talk about the application. Okay, so maybe before talking about the application, let me tell you briefly that the BCS theory, these we talk about the low temperature superconductivity. So, BCS theory, the main ingredient is what is known as Cooper pair. So, you have in your circuit you have electrons passing through this, which will be responsible for the current. So, in BCS theory, if two electrons, because they are oppositely charged, they will repel each other. But in BCS theory, they came up with this idea of Cooper pair, which tells you that these two electrons, they don't repel. Instead of repel, they form a combined object, which is called as Cooper pair. So, electrons are fermions, but when two electrons form this Cooper pair, they become boson. This is called composite boson. So, this composite boson, when it passes through the material, it faces almost no resistivity, and therefore, it can carry current, right. Okay, so, that is the idea for the superconductivity. Now, this Cooper pair, what it happens, because it has energy levels. So, one is high energy level, one is low energy level, and so you can use, so these energy levels are distinguishable. So, you can use it for a what is known as a 2-level quantum system, what these days we call as qubit, okay, 2-level quantum system. And this qubit, this is called superconducting qubit. And these qubits are the building blocks of what is known as, quantum computers, superconducting quantum computers, and that, you can use in places like, I think IBM or whoever is building their quantum computer is based on that. There are other applications also for in quantum optics, light matter interaction, all these things you can use this, these macroscopic quantum tunneling there. Okay. Yeah. So there are other applications, but I just confine to this only. Yeah.
If there is no question, I will ask one. Crazy question, is Big Bang a macroscopic tunneling?
Yeah, I'm not sure because that is it is so the evolution from Big Bang is a deterministic evolution, I would say, right? There is no alternative that after Big Bang what has happened. There is only one story. So tunneling is a probabilistic effect. Okay, so it can happen with certain probability, not with 100% probability.
So this might be an absurd question, but we say there is superpositions of state, and then we also say measurement will, collapse the superposition of the states, and then we'll have only one state. Then what makes us believe that there are superimposed states? Why do we say that there are two states existing at the same time when we cannot really measure it?
So if you don't, consider existence of superposed states, right? Then what happens is that, let's say I take a spin half particle or photon polarization. It can be, either up spin state or down spin state, and as I said, quantum mechanically you can have linear superposition also. But if you measure spin half particle along up spin, along z direction, it can be up spin or down spin. But the same spin half particle you can also measure along x direction. So you put your magnetic field, inhomogeneous magnetic field, along x direction. So there, this up spin and down spin component will give equal contribution to that. And if you don't assume superposition to begin with, you cannot explain this result when you measure along plus x and minus x, like up x and down x. Okay, so superposition is necessary for that.
Yes. So all the examples you gave were discrete bases or discrete states. Are anyone working on continuous basis? So
no, quantum mechanics of course holds for continuous basis. No doubt.
No, I'm saying for macroscopic systems.
Macroscopic, yes, in principle, yes, it can be done. Yeah. In fact, they have also done.
Okay.
So in fact, in order to describe macroscopic superposition, you need to go to a continuous reference frame. Otherwise, it will not work. Okay.
Sir,
I got just one question, because already in the Josephson's effect, it's also macroscopic effect, right? Josephson tunneling.
Josephson tunneling, no.
It's also macroscopic, it's not macroscopic
because
tunneling.
it's a single particle. Basically, it is a Cooper pair which is passing through, a single one. So Josephson tunneling is not a macroscopic effect.
It's not macroscopic tunneling.
It was prerequisite for their experiment. This last year, 1980 is their experiment. But it is Josephson tunneling per se is not macroscopic effect.
But since you are observing a current or something like that, large number of Cooper pairs should be there.
No.
So in that sense, it's not.
No, because it depends how much current you are absorbing. Okay. You are absorbing how much current. Okay.
So is it not macroscopic in that sense?
No. See, the thing is, there are photodetectors. Single photon can go through, right? And there will be current in that detectors. Okay, that is how it is detected. So these days one can actually detect effect of single photon. So by looking at the current, amount of current, you can decide whether it is single photon, two photons, or a macroscopic object. So that one can do. Yeah.
So it was a very amazing talk, sir. It was very interesting. I have a question. Like when you are talking about superposition, you said superposition is observed in C60 molecule, right? So
C60.
I didn't get it. So can you?
No. I talked about this Young's double slit. So you prepare C60 molecule, okay, in some state, and send through one by one through these two slits. you get interference pattern. And this interference happens because of superposition. Because interference cannot be explained without superposition.
Okay, so you were saying about the interference of the C60 molecule.
Not C60 molecules, states of C60 molecules.
Sorry?
States of C60 molecules.
Okay.
Yeah.
And then another question, it might be silly, about the Schrodinger's cat. So, can we say that the cat and the radioactive particle are entangled? Like
that's what I said. The state that I have written is the radioactive particle in its state, whether it is decayed or not, and cat state, like alive or dead, they are entangled.
Okay.
They are correlated. Yeah.
Okay. Thank you, sir.
Thank you.
Sir, I just want to ask about your thoughts on another theory. Universe interpretation, there is another thing where it can be, the quantum state can be determined. So, I just want to ask whether, what would be the wave equation for that, like Schrodinger's wave equation in terms of quantum?
I don't think many world interpretation has Schrodinger-like wave equation, because once you have Schrodinger-like wave equation, and you have this probabilistic interpretation, that will be, so basically many world interpretation, it's a deterministic process, right?
Yeah.
So you cannot have anything probabilistic in nature there, when you talk about the measurement. So something modified to, so basically you can have Schrodinger equation, but it should have some other parameter which will tell you that if you measure, then you will deterministically get this outcome.
So are they in superposition in many worlds also, like if a cat is dead and alive, so the cat can either, like in one world the cat is dead and another world cat is alive?
Maybe, I am not much familiar with many world, but yeah, it can be,
Okay.
possible. Yes.
Thank you.
Okay, I guess it's time for coffee. It has been a long day. I suppose I would like to thank on behalf of all of us, Professor Vijayan and Professor TGH, as well as all the speakers. Let's give them a big hand.